Internal block schematic of an op-amp. An op-amp has two input terminals, one output terminal. Input 1 and input 2. Input stage, intermediate stage, buffer and level shifting stage, output stage. Input stage. The input stage requires, this is the input stage requires high input impedance to avoid loading on the sources. To avoid the loading on the sources, the op-amp requires high input impedance. It requires two input terminals. It requires two input terminals. It also requires low output impedance. To avoid loading on the sources, the op-amp requires high input impedance. It requires two input terminals. It requires low output impedance. All such requirements are achieved by using a dual input, balanced output, differential amplifier as the input stage. Dual input. This is dual input means VS1 and VS2 are the two input signals are applied to differential amplifier configuration, and balanced output differential amplifier. Balanced output means the output is taken across these two collector terminals. The function of a differential amplifier is to amplify the difference between the two input signals. The differential amplifier has high input impedance. This stage provides most of the voltage gain of the amplifier. Dual input, balanced output, differential amplifier. This one is the dual input, balanced out. Input stage of operational amplifier is dual input, balanced output, differential amplifier. The most of the achieved by using this input stage. In order to avoid the loading effect on the sources, the input is where ideal op-amp is very high. In practical case, it is infinity. Ideal case, it ohms range. So another requirement is output resistance should be low. Input impedance is very high. Avoid the loading effect on the sources. Output impedance is low, and also it requires two input terminals. Terminal 1, input 1 and input 2. Next stage is intermediate stage. Intermediate stage. The output of the input stage drives the next stage, which is an intermediate stage. First stage output drives the next stage of an op-amp, that is called as an intermediate stage. This is another differential amplifier with dual input, unbalanced, that is single-ended output. Like first stage, the intermediate stage of an op-amp is dual input, unbalanced output configuration. The overall gain requirement of op-amp is very high. That is, in ideal case, it is infinity. In practical case, it has high value, 2 into 10 power 5. The input stage alone cannot provide such a high gain. The main function of the intermediate stage is to provide an additional voltage gain requirement. The intermediate stage provide additional voltage gain. Practically, the intermediate stage is not a single amplifier. This one is intermediate stage. Intermediate stage is not a single differential amplifier, single amplifier, but the chain of cascaded amplifiers called multi-stage amplifiers. Chain of cascaded amplifiers, that is called as multi-stage amplifiers. Multi-stage amplifiers. Intermediate stage means dual input, unbalanced output. Dual input, unbalanced output means the output is taken across the only one collector terminal. Next, level shifting stage. Third one is buffer and level shifting stage. All the stages are directly coupled to each other. Stage 1 and intermediate stage all the stages, intermediate stage includes the multi-stage amplifier. All the stages are directly connected with each other. No coupling capacitors are used. All the stages are directly coupled to each other, as the op-amp amplifies DC signals also. The main function of a coupling capacitor is block the DC signals, Here there is no coupling capacitors, therefore DC signals are not blocked. The DC signals are also amplified. Hence, the DC quiescent voltage levels of previous stage gets applied as input to the next stage. Hence, stage by stage DC level increases. DC level is also increases. Therefore, the stage by stage DC level increases well above ground potentials. Such a high DC voltage level may drive the transistor into saturation. As the DC level shifts, the operating point moves towards the saturation region. This further may cause distortion in the output due to clipping. If the operating point moves towards the saturation region, therefore output is not amplified, some clipping is appeared. Some clipping is there. Hence stage by stage DC level increases well above ground potential. Such a high DC voltage level may drive the transistor into saturation. This further may cause distortion in the output due to clipping. Distortion is produced at the output. This may limit the maximum AC output voltage swing without any distortion. Hence, before the output stage, it is necessary to bring such a high DC voltage level to 0. Bring back to original position with respect to ground. The level shifter stage brings the DC level down to ground potential when no signal is applied at the input terminals. Then the signal is given to the last stage, which is the output stage. After level shifting stage, the output of the level shifting stage is given to the output stage. Bring back the DC level is bring back to the original position. The level shifter stage brings the DC level down to ground potential when no signal is applied at the input terminals. Then the signal is given to the last stage, which is the output stage. A buffer is usually an emitter follower whose input impedance is very high. This prevents loading of the high gain stage. Next one, level shift stage in op-amp. Generally, coupling capacitors are not used. Coupling capacitors' main function is to block the DC signals. But in case of all the stages are directly in op-amp, directly connected to each other, therefore DC signals are also amplified. As coupling capacitors are not used to couple the amplifiers in the intermediate stage, the DC biasing voltage levels propagate through the amplifier chain. This finally appears as a significant DC component at the output along with the AC output. Follow are the effect due to such DC components at the output. See, the output gets distorted output due to additional DC level. Due to amplifying of that DC signal, the output is waveform is shifted like that. Due to shifting of the DC level, the operating point moves towards the saturation region. Therefore, some clipped output waveform is appeared like that. The main purpose of the level shifting stage is to shift the output quotient DC level towards the ground. Due to direct coupling effect, the DC level is shift like that. In order to bring back to original 0 level, we use some shift level shifting stage. Level shifting stage bring back to DC level value, that is 0. To shift the output quiescent DC level towards the ground with the minimum change in the AC signal. This is also satisfies the requirement of op-amp, that its output should be 0, should have quiescent voltage level of 0 for 0 input signal. This is the simple level shifting network. V in, VBE, R. Apply KVL. The simplest type of level shifting network is shown in figure. This one. It is basically an emitter follow circuit. In the circuit, observed in the figure, this figure, the amount of shift obtained is equal to VBE. This is the VBE, which is almost 0.7 volts. So if VM is Vin is increased level signal, and V0 is the output with reduced level. Vin is increased level and V0 is the output with reduced level by an amount VBE. We can write for the above circuit, V0 is equal to Vin minus VBE. The negative sign indicates downward shift in the level. Next, output stage. Last stage is output stage. The basic requirement of the output stage are low output impedance, large AC output voltage swing, and high current sourcing and sinking capability. Low output impedance means R0 is generally 75 ohms. Large AC output voltage. Large AC output voltage swing means this one, output voltage swing without any clipping, and high current sourcing and sinking capability. The push-pull complementary amplifier meets all these requirements and hence used as the output stage. Generally, push-pull complementary amplifiers require such a the push-pull complementary amplifier meets all these requirements. All these requirements means low output impedance, large AC output voltage swing, and high current sourcing and sinking capability. Hence, used as an output stage. This stage increases the output voltage swing and keep the voltage swing symmetrically with respect to ground. The stage raises the current supplying capability of the op-amp. In short, the overall block diagram can be shown in figure. Stage 1, intermediate stage, level shifter stage, output stage. Stage 1 is input, stage 2 is intermediate, stage 3 is level shifting, stage 4 is output. These are the input. Some stages are present in the operational amplifier. Fourth one is an emitter follower output stage. Low output, it provides low output impedance. Input stage is the differential amplifier configuration. Differential amplifier input stage, the base terminals of two transistors acts as the input terminals. Currents and impedances. Generally, practically an input stage is a transistorized differential amplifier stage using the two transistors. The base terminals of these two transistors are the two input terminals of the op-amp. Some small DC base current is necessary to maintain the operating state of the transistor, not zero. Generally, in ideal case, these two base currents are zero. For operating point setting purpose, we need some base currents. These two base currents are the input bias currents of the op-amp. Typically, the DC input current is of the order of 500 nanoamperes. The input impedance Zin is very high of the order of 1 megaohm or greater. To increase the input impedance, field effect transistors are used instead of bipolar junction transistors. In such a case, gates of the two FETs are the input terminals of the op-amp. The output stage is an emitter follower having low output impedance. The output impedance Z0 is usually 75 ohms, and the maximum output current is of the order of 25 milliamperes.